if I forgot to push the record button, please remind me, because it will be such a waste if I give a whole lecture but without recorded. This will be a waste of time. All right, so suppose it should be fine now. So let's start our lecture. Okay, yesterday we talked about the definition of the stress. Okay, and then we noticed that we need to capture the segment of a bar. That's the reason. The reason is that because when we apply a concentrated load, it will give us a really high, very high stress at the tip, at the location that we apply the force. And then it will, so this is a very complicated stress status in this region, okay? But after some distance, you can see that the stress become uniform. You can imagine that this is kind of the water source and pour into the tube, and then the tube eventually will have uniform flow in the middle. So that's the reason why we take the definition for the stress is using the middle section, okay? And the most importantly, you need to know that stress is the localized value, the localized response. So you can see that even in the same material, they may have different stress status at each point, all right? So you see this is stress-free, sigma x equal to 0. So this area, because the water flow, the stress flow is not flowing to that position. So those position feel nothing. So it has stress-free status. So please don't think that, oh, this definition, sigma equal to P divided by A, and everywhere is P divided by A. No, it's not constant, okay? So only this part is uniform. So, okay, you can say the stress is uniform and the constant T divided by A, but at other position, no. Okay, this is a really important concept I would like you to remember, okay? And also the strength. Strength is really easy, just the deformation rate, okay? The elongation rate. So you can use in the percentage, 生长量缩短量, no, 生长率缩短率, okay? So this is a rate. So if you are using the rate term, you don't have any unit, okay? So this is really important concept. And final concept I mentioned yesterday is that if you want to take a look, determine the stress at any point in the material, just cut that position. Just cut that and split it. And after you split it, and you need to understand that every position in the materials in this course are all in equilibrium. Yeah, they're all stable, so they won't fly away. Okay, so if you cut it and you still draw the force on the part that you separated, and you will notice that you should draw something at that section you cut. Otherwise, this part will fly away. Okay, so you can see that, yes, this is the force and the force weight. Yeah, okay, for the weight and the force due to the self weight. So these forces are all are all there, right? Are all there. So if you cut that and then you separate that, and the force are there. If you don't do anything here, this part will fly away. So you need to apply, or you need to plot a force which can balance to make this part equilibrium again, so that you can determine the force at that location. And if you have force at that location, you divide by area, and then you can know the stress at that location. So that's the concept logic flow. I hope you can understand what I'm talking about. Okay, so here, F mix. Okay, this is really important. And then, how about the other part? How about the other part? The opposite part here. You can remember that everything is in equilibrium, right? But if you cut it, you have a force F mix in this in this point. So suppose this point has a opposite force and with the same magnitude, because they are opposite, okay? And also, you can imagine that. Do you think this part is equilibrium? It doesn't look like that, right? Because you only have one force and this part will fly away, right? No. So suppose then how to make it equilibrium? Because this ceiling, the ceiling up on the top will provide the fixation, will fix that. So it will give the reaction force. So the reaction force are, you know that the R must be equal to F mix. Okay? Now, so you can imagine that this R is actually equal to F mix, and the F mix equal to everything below. Okay? So do you think F mix is come in front of your eyes with from nowhere? Well, why we cannot see F mix in this figure? Because if you combine them back together, the F mix, this point and this point overlap, and F mix and F mix cancel each other. So it becomes internal force. Okay? So if you combine them together, the F mix, two F mix will cancel each other because they have opposite side, opposite direction. So you cannot see anything if you don't cut it. Okay? This is really important concept. So again, if you want to see any stress, any force, internal stress, internal force, at any location of the material, you just cut it and separate that and balance both one of the side. You can balance one of the side, and then you can determine the value, or you can balance both of side, and you can determine it. So yeah, so let's continue. So if you does this side help to solve the F mix? No, because we don't know R as well. So we can only use the bottom part to solve the F mix. Okay, so F mix equal to W, no problem, right? And W0, right? W0 is self weight. And you notice that I use the same color. Okay? And Let's continue. W plus G gamma AL. Gamma is the density of the bar, okay? And AL is the volume. So you can have the mass. The mass times the gravity G is the force, okay? So W plus gamma I D square 4 LG. So you got F mix. So sigma mix is F mix divided by A. So W divided by A plus gamma LG equal to 4 omega I D squared plus gamma LG. That's it. So sigma max is 4W divided by pi D squared plus gamma LG. Right. That's it. So now you can imagine that every point in this bar may have different stress value. Okay? May have different stress value. And you can imagine that sigma max and then slowly decrease. Slowly decrease. All right. And this is not stress zero. Only if this point is stress zero, only if there's no weight underneath. All right. Good. I would like to yeah, so I will give you time to write down all these notes. When I was kids, like your age, and I start to learn mechanics of material. At that time, I found really difficult. I found this so complicated that I cannot understand. And then I found, and when I become a professor, I start to prepare this all the teaching material, and I found that the reason why I didn't study this course quite well because some important concept I didn't understand thoroughly. Okay, I didn't understand thoroughly. Like this concept, if you want to get the force or stress, internal stress or internal force, you cut it, and then you separate it, and you do the force balance. So because I didn't understand this concept, so it makes the later or more difficult. But if you understand this concept, you can help. You can just using one concept to solve a lot of problem. All right. Right. After this problem, we are going to enter in a part that introduction of material science engineering taught you before. Okay. Actually, I believe all of you heard of the stress and strain term. 可以帮我关一下门吗？谢谢。来 ，OK，谢谢。Right, next, this part and the later part become the later part is actually something you already know. So I just give you some emphasis to strengthen your background of the background knowledge for this. So maybe you should say why we use stress and strain, strain and stress. Why? When we did when we were in senior high school, we used displacement and force, right? force, you move an object, and the displacement. So this sounds okay, right? Displacement and force is actually okay. Why we use strain and stress? Because the reason why is that Galileo, okay, he did an experiment. He did a tensile test. So the sample A, B, C, D, the area, well, the sample was different shape, geometry, okay? And the material is 3 steel and 2 aluminum, all right? So you just do the tensile test and measure the load and displacement. This is the result, okay? The result is that 5 devices give you 5 lines, 5 curves, 5 lines, okay? So Galileo thinks that can we get properties that belong to material itself rather than and exclude the geometry effect. I want some property that only belong to that materials. Even you change their shape, it still belong to the material. So he found that if the load divided by the cross-section area of that device and the x-axis, it changed the displacement or elongation into the elongation rate or percentage, which means strength. Okay, they found that the fine lines become 2. So steels were all overlapped. Sorry, this one. Alumina will be only 1 lines. So you can see that strain and stress can exclude the geometry effect. Okay, so that's the reason why we are going to use strain and stress. Otherwise, if you once you change the shape and you need to measure everything all over again, this is not efficient. Okay, so we need to do the mechanical property of the material, and we sometimes, well, typical, we do the tensile test, compression test. So we followed ASTM, should be American Standard something. Okay, wow. Why at ASTM? Because American USA is the biggest country in the world, so we follow their rule. And also, typically in this course, we talk about the static test, which means that the loading increase slowly. So you can regard every step, every time step of this test, the material is always at equilibrium state. Okay? So the increment slowly, so slow that the material doesn't change there dramatically. Okay? So yeah, this is a simpler way. But dynamic test, which means that the loading increase quickly, so the property may related to the impact or shock wave, something like that, or gunshot, bam. So these properties are all related to dynamic tests. But we are not going to talk about this. This is more complicated. And we just considering that loading is there and static, quiet, not moving. And let's see. So for example, you see the building. Our human being weight is not significant, right? So we can regard it if we considering the building safety. We typically just say, okay, the floor itself, the weight floor itself, or some big machine or big cars or something like that. So stay there, and then we just do the design. Should be okay. Anyway, tensile test, we have some rules, and this is not a really important in this course. All right. So next, we have a navel breast tensile test. Let's take a look. I believe you saw this video previous, and then you all know what will happen. So after the tensile, you see the necking occurred, and then finally break it. And then you can see that after the bound, so which means that the energy released. Okay. Right. So let's considering, yeah, this is the section. All right. So during that test, some properties has been measured or recorded or write down in the table. So we need to talk about the normal and true stress and strain. Nominal. Nominal means everyone think of that. Everyone agree with that. Okay, or simpler one. So nominal stress, also called conventional stress or called engineering stress. Okay, so which means that when we talk about sigma, previously we write out sigma equal to P divided by A. But if we want to okay, so normally in our course we only talk about engineering stress or engineering strain, what we call nominal stress or nominal strain, because it's easier. Okay, but actually in the real world, if you really want to discuss really complicated problem, actually you need to talk about true stress and true strain. Okay, the reason why is that because when you do the tensile or compression, actually your cross-section area will change. But because the change is too small, so typically in a simpler way, we just divide the initial area of the cross-section, A0, or we talk about initial length. Okay? But in the real definition of the stress, true stress, you need to calculate the stress at that time, at that particular time, there's area has been changed. You need to divide that area. So it will be really difficult when you calculate it by your hand. Okay. So in our course, we're using this two. All right. But we still need to give you some concept for true stress or true strain. Okay. Let's take a look. So you can say sigma true equal to P divided by A, then, and A is the actual area at that particular time. Wow, that's really difficult. So A is changing. And the L is the actual length at that, at that time before, a little bit before dt. Okay, so this is a little bit weird. So let's take a look. So you can imagine that when you have A no, sorry, when you have A no, L no, which means that the bar before the loading. But if you have a force applied to P, you can think of that. You must start from 0 to P, right? So when you go into dp a little bit, and the L no become maybe L no plus dl. Okay, so after the P, after you finally reach the magnitude of P, actually your actual gauge length is become L, and then you increase to P, you will have the final step of delta, and then you need to determine that the epsilon T. So this is really difficult, okay? So how can we do that? We need to sum of all the instantaneous strain. Okay. Okay. And epsilon T is actually equal to the sum over all the strain, right? Every instantaneous strain, every tiny step, tiny strain, you need to sum it all together. So epsilon T is equal to integration of the epsilon. And what is the epsilon? It must be dl divided by L. And the L is changing from L0 to LF. L0 is initial length. LF is the final length. Okay? So you can imagine this is quite complicated. And after you do the integration, natural log LF divided by L norm, which is equal to natural log L0 plus delta. The delta is final length. Final displacement, total displacement. So natural log become 1 plus epsilon engineer value. Okay. So okay. So I hope you can understand how the true stress or true strain definition, how we define that, how we define those two properties in a true actual condition. Okay, so you can see that. Let's compare engineering strength with true stress and true strain. Which one is greater or which one is less? Okay, you see A0, epsilon engineer and true strain. Sorry. Engineering stress and true stress. Which one is bigger? You can see that in the tensile test, when you elongate the bar, the area may shrink, become smaller, right? So A0 is greater than A. So the A is smaller, A0 is bigger. So epsilon T is greater than epsilon E because A0 is bigger. Sorry, A0 is bigger. And then epsilon E and epsilon T, which one is bigger? Because the actual gauge length L is greater than initial gauge length. So L greater than L0. So it will be reversed, that epsilon E greater than epsilon T. Okay, so that's their relationship. All right, I hope you can get this. So once we understand the definition for engineering stress, engineering strain, or true stress or true strain, then we can introduce our stress strain diagram in the next page. Next one. Stress strain diagram of the structural steel. Okay. Sorry, this is not to scale, not to scale. So we draw here is just for you understand all the steps. Okay. So y-axis is sigma stress, and the epsilon is the x-axis. Okay, so when you apply the force and then elongate it, it starts from the beginning of the origin, right? And you can expect it that when you pull up, and then it will increase the stress and strain with proportionally increase, okay, with the value, with and of course you will know that this is a Young's modulus later on. And then at some point it exceed their proportional limit, which means that they are not linearly proportional anymore. They are not linearly dependent. It becomes the curve. Okay, so it starts a little bit, maybe we can, it become a little bit, it's maybe it's not linear, it's a kind of the a curve maybe. Okay, and after that it become yield. So which means that you don't need to pull hard of the stress. It will increase their strength dramatically because it yield. Okay, but if it exceeding the the yielding stress platform, the stress may increase again, and the structure of the material will change because such great loading. So it will has its own strength again. Okay, doesn't like this. So it was become hardening. Okay, strain hardening. You see that? So you can imagine that a city or a castle. Okay, so an army need to attack that castle. Okay, so they attack, and once it win the battle, and the castle yield, so it will give you all the all the money to the army, right? But if the army is too bad, it still gets the money, and people in that castle cannot eat or has no food. They will revenge again. They will come together and fight back again. So that's the position. That's the hardening of okay. But if the army is still really good, really powerful, and the castle cannot stand that, so after the second battle, they will lose. Wow, wow. Okay. And during this echo necking, and I believe you all see that in the video, that okay, the necking and fracture later. Okay, so I will say this curve is nominal stress because A naught is used. You can notice that when you do the necking, when you discover the necking procedure, you will see that the A become really small, right? So if you using the curve of the true area, true stress, real area is used. So you can imagine that this necking, or even here, the area shrinked. But if we use original area, the curve like this, if you use real area, actually sigma T true stress should be greater than the engineering stress. So you have different, sorry, you have different curve to the final point, because you can see that the area here becomes really small, all right? And of course, this linear region is what we are discussing, okay? We always discussing in the linear region. We are not discussing this, okay? Which we only need to know the concept. We only need to know the knowledge. But when we describing the safety design of the application of material, we typically focusing on this linear region. Easy. Okay? And notice that this is not to scale, not to scale. Okay? 我刚刚讲的那个例子啊，其实还蛮无聊的哈。总之就是我怕大家听不懂，就是如果有个村庄被敌人攻击了，然后敌人攻击他，他一开始可以互相就是打好打满这样，但是发现哇敌人太强了，他就只好投降了，所以就交出他的所有的财富了。结果没想到那个敌军太坏了，他连他们的平常吃的食物都要把它抢走。那些人就会觉得说，我不能，反正我都要死，所以我就要赶快变成另外一种状态，就是狂暴的状态。他们就会改变他自己的微结构，也就是说，原本不想打仗的，但是他也想打仗了，这样类似像这样的哈，然后他就又变强了。但如果敌军还是以压倒性的胜利的话，压倒性的攻击能力的话，他终究还是会失败啊，就还是说死掉了。也就是说，村庄是整个被屠城了，就大概是这样。这就是一个大概材料跟世界上可能有稍微相关的地方。Okay, now let's talk about the not scale. The real scale looks like this. Wow. So you can see that the yield platform is actually small compared to the hardening. Okay. Right. So what we talk about, the metal or steel or aluminum or something, they are all ductile materials, which means that they can have very large permanent deformation before failure. So after the linear proportional or yield, after the yield point, the material may have permanent deformation. I will explain this later in more detail. So which means that you can see a lot of region that allowing permanent deformation. So you can have large permanent deformation before failure. A brittle material, yeah, brittle material has no significant platform of this yield platform. So it just broke. Okay, just like glass. So you can see that the proportional limits after the proportional limit show a really little reduction of cross-section area. So area cannot be reduced. So it just break immediately. Right, so this brittle material and ductile material. I believe you all know that in introduction of material science and engineering. Okay, so next, stress strength diagram that typically for material you bought it in the shop. Okay, the shop will tell you, oh, this material has yield stress equal to blah 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 blah. but some of the material is difficult to measure the yield stress. So we typically using offset method to define yield stress. For example, if there is a if there is a curve like this, okay, and the curve has no significant yield stress platform, okay? So how can we define the yield point? This is just a rule. Don't ask me why. So the engineering field, they think, okay, so we can define a 0.002 offset. What does that mean? You can use the slope of the linear region and right shift to 0.002 strain. So this 0.002 is kind of convention. We don't know why. Okay, it's just a rule. Okay, so because it's difficult to measure, define the yield point, so we just give the, okay, you shift to 0.002 and then you get that point, and then you get sigma y. Okay, so this is just define. Okay, because we cannot find the proper sigma y, so okay, we just choose this offset method to get whatever value. Okay, right. And another concept I will give you is that the strain curve for material under compression and tension are not symmetry. Okay, are not identical. Okay, so you see that it may looks like this. So their behavior are totally different. Okay, so you can see some of the material is good at tensile, but bad of compression. Okay, bad of so what kind of material it is? Concrete. Okay, our concrete is good at tension, but bad of compression. Okay. Sorry. Sorry, I made a mistake. Concrete is good at compression, but bad of tensile. Sorry. Okay. So that's the reason why we need to reinforce it, make it stronger, by putting some steel in the inside the column. Okay. So steel is good at tensile, but bad at compression. But the concrete is good at compression and bad of tensile. Okay. So these two materials combined together, so we can build up a really tall building in the modern city. All right. So let's talk about loading and unloading. When the stress strain curve returns to point O along the original loading after unloading, which means that the material is under elasticity region. Okay, elastic region. So you can see that elastic region is not always linear. Okay, so in this case, there's no linear region. Okay, the curve is all round, not linear, but they can still have elastic region. So which means that if the loading here from here to A and come back to original place, origin, which means that it is elastic. Okay, but if it exceeds some point, it called elastic limit. Elastic limit. After the point E, at point E, it's okay. Come back to O. But if you load into exceed the electric point, so not electric, elastic point E, it will come back to a point that's along the initial slope. Okay, so for example, if the loading come to, well, maybe A plan, maybe, and the A plan will go back to here. Okay, so this point is exceed elastic limit, so it can no longer go back to the original origin. So it will follow the same, typically they will follow the same slope of the initial slope and go back to the region, the point. And the point, the distance between the point of and the origin is residual strength. So you can see that the residual strength can increasing, okay, can increasing. So if you start again loading here, it will go from here, and then C to B, it will go back to the residual, the residual strength will increase and increase and increase. So you can imagine that the curve will be da-da, 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 and increase, increase, increase. Okay, so this is elastic recovery, but the residual strength will keep pushing, pushing and pushing. Okay, so it's called plasticity. Okay, plasticity, because the plasticity means that the shape is completely changed forever. Okay, so this is actually what we explain. So loading, unloading, loading, unloading, loading, oh, unloading, and then loading, unloading, loading, unloading, loading, unloading, loading, unloading. All right, so the region become it keep pushing to the right. Okay, and finally, this figure I have talked about that, but I should just provide provide the curve. This curve I have mentioned in the previous few pages. Okay, so that's it. I think I finished the concept of the stress and strain curve. Okay, and next week I will introduce more calculation parts. Okay, so I will see you next week. Thank you. Bye bye. If you have any questions, just come here. All right. 记得上 Facebook 哦，会有一些公告还有资源。OK。